recall the definition of a Nash equilibrium. A strategy profile is a Nash equilibrium when every player is playing a best response to the strategies of the opponents. So, in order to write a mathematical program to find a Nash equilibrium, we start writing the best response problem of a generic player I. Here the best response problem of player I. Player I maximizes error expected utility, subject to the strategy of player I is well defined. Notice that the best response problem of player I is linear, since the variables are only the strategies of player I. When searching for a Nash equilibrium, we need to solve simultaneously the best response problems of all the players. That is, we need to solve simultaneously multiple maximization problems, but we don't know how dealing with these problems together. Indeed, we can just deal with problems with a single maximization or minimization. The first step is to study the dual problem. Here we have the dual problem. The objective function is vi, that is a scalar. Here are the constraints, requiring that the value of vi is not smaller than the value provided by every action of player I. The dual problem is a linear minimization problem on variable vi. Recall that in linear programs, primal and dual problems are equivalent. However, if we combine all the dual best response problems of all the players, we obtain a combination of minimization problems that we are not able to solve. In order to produce a problem that we can solve, we do the next steps. Start from the primal linear maximization problem. Consider also the dual linear minimization program. We can combine them using the complementarity slackness theorem, obtaining a set of constraints without any maximization and minimization. Here, the set of constraints. We have the constraints of the primal program. We have the constraints of the dual program. We have the complementarity constraints that are satisfied only when the solution is optimal for the primal and the dual program. This constraint forces either the strategy on action AI to be 0 or the value given an action AI to be equal to VI. That is, equivalent to say that action AI is the best response for player I. If we put together the complementarity slackness conditions of all the players, we obtain a feasibility problem without any minimization or maximization. In the specific case of two players, we have this linear complementarity constraints problem. We have a set of linear constraints and a complementarity slackness constraint in which we require that at least one of the two terms in red is equal to 0. Linear complementarity programs can be solved by using the Lemke algorithm. In particular, this specific program can be solved more efficiently by using the Lemke-Hozon algorithm. However, this algorithm is not implemented in commercial solvers for linear and mixed linear program. So an interesting question is whether we can formulate this program as a linear mixed program and thus using commercial solvers. Here we have a mixed integer linear program finding a Nash equilibrium in two-player games. Thus, we can solve it by using commercial solvers. This set of constraints is the same we have in the linear complementarity problem. We have a new set of variables, bi, one variable per action that can assume binary values 0 or 1. The meaning of these variables is that if an action AI is played, then the value of bi AI is positive. Technically speaking, we say that if an action is played, then it is in the support of the strategy. In our case, if an action is in the support, its BI value is positive. This set of constraints substitute the complementary conditions. These constraints force the strategy on an action to be 0 when the value of BI is equal to 0. That is, when it is not in the support. While when BI is equal to 1, the strategy can be any. Consider this constraint. Consider the case in which the value of BI AI is equal to 0. The orange term is smaller than the green term. Since the green term is a large constant, the constraint always holds. Instead, when the value of BI is equal to 1, that is, when the action is in the support, the orange term is equal to the green term. This means that if BI is equal to 1, and therefore the action is played by the player, the action must provide an expected utility equal to VI. That is equivalent to say that the action is a best response. We can use mixed integer linear programming to find a Nash equilibrium maximizing a linear objective function. For instance, we can maximize the social welfare, that is the sum of the expected utility of the players. This can be done easily by introducing an objective function, as remarked in red. Furthermore, we can slightly modify the mixed integer linear program introduced before to find an epsilon Nash equilibrium. This program is the same we had before, except that we allow that the actions played by a player are not necessarily best responses, but they could provide a regret of at most epsilon. Since no action provides a regret larger than epsilon in the program we define in the slide, we have that the regret of a player cannot be larger than epsilon. This is because the regret of a player is the convex combination of the regret provided by the actions the player plays.